Good evening everyone. My name is Renu Raman Sahu and today we will be discussing about the concepts that the professor discussed in the last week uh, and it was about the energy bands, chronic panning model, and based on this we'll discuss how the band formation takes place and then we'll talk about the semiconductors. So uh, in the last few classes what we were doing was we saw qualitatively how the electron waves or the de Broglie wavelength of the nearly free electrons uh, when it matches with the wave vectors associated with the periodicity of the lattice, then it gives rise to the diffraction of those electron waves, and hence, yeah. Hello, are you able to hear me? Uh,
Yes, sir. I can hear.
okay, yeah. So we just started. Uh, Maybe. Yeah, not in You went through the previous classes. I mean
Yes, sir.
the
Until last week, yeah. This week, this week,
yeah, yeah,
yeah.
sure. You were able to solve the problems, right?
Yes, I could. Yeah.
Yeah. So what we're doing till the last class was we saw that we saw in a qualitative way the formation of energy bands, and we attributed it to the uh, diffraction of the electron waves, which are the nearly free electrons. Okay, and what we saw was that this and what we saw was that the k vectors associated with the electron waves, and when one end of it touches with that Brillouin zones and the Bragg planes, it gave rise to diffraction, and that gave the distortion in the energy. What we'll be doing today is we will try to see this. So we'll take a periodic well potential and we'll try to solve for its energy. We'll try to see the band formation or the energy band formation quantitatively. Okay, so to solve for this potential, what we will be doing, we'll be solving the Schrodinger equation or the Schrodinger wave equation for this particular potential. And this particular approach is called, this model is called the chronic penny model. Okay, so what we are saying is, so let's say that this is the so you have a periodic potential with periodicity A. So this is your one periodicity, and the well is of width C, and this is C, and this from here to here it is B. So so that means if you take this as the origin, this will be A minus B, this will be A, this is like A plus C, and here it is minus B minus A. You are able to visualize this, right? And on the y-axis what we have is the depth of the potential. So we take the base or uh, the depth to be 0. If this is at 0, the height will be v naught. So this is the setting that this is the potential which we want to solve. Okay, so it is a bit mathematically involved. So what I'll be showing you is the mathematical outline what we are going to do. So we will be starting with the Schrodinger equation. So this is your Schrodinger equation for the potential. So when v equal to 0, when is v equal to 0? V is 0 in the regions from 0 to a minus b. These are the regions where v is 0. So when v equal to 0, so the Schrodinger, this is the starting equation. From this equation what we have is, we put v equal to 0, then we are left with this minus h bar square 2m double derivative of the wave function with respect to the x, and that is equal to e psi of x. And when we take all this to the right hand side, so d2 psi over dx square is equal to minus 2me by h bar square. And so this you have to think of it as a positive quantity, 2me by h bar square. So it is like a harmonic oscillator equation. a differential equation for the harmonic oscillator. So psi of x is equal to a e to the power I beta x plus b e to the power minus I beta x, where a and b are arbitrary constants that needs to be determined, and beta is root under 2m by h bar square. So this just comes from the harmonic oscillator solution to the harmonic oscillator differential equation. So now this was when v was equal to 0. When v is equal to v naught, when v equal to v naught, what we have is, we will just have this v of x, we will replace it with v naught. V naught is a constant with respect to x. So what we did here is, just we took this particular term to the right hand side, so it is e minus v naught, and the rest like the previously we did. So 2m by h bar square we took to the right hand side, and we are left with this equation. So now we see that, okay, let's say that the energy is less than v naught, and this is a positive quantity. So this differential equation is satisfied by this psi of x equal to c exponential alpha x plus d exponential minus alpha x, where alpha equal to 2m v naught minus c over h bar square. Okay, and c and d are arbitrary constants that needs to be determined. So now we have the solutions for the regions where v equal to 0 and v equal to v naught. Now what we are going to do is to look at the nature of the solutions, how the solution psi of x should look like. The first requirement is that the psi of x should be continuous. That means, for example, let us say that at x equal to 0 is, notice that it is this point. At x equal to 0, the wave function from the left hand side of this point 0 and from the right hand side 0, the wave function should match. That means sin naught of 0, sin naught is what? The wave function where potential v equal to 0. That means you are taking, you are going from the right hand side, this limit you are taking, that should be equal to psi v0. That means psi v0, so psi v0, it denotes the value of the wave function where when you approach from the left hand side, or where the potential is v. Similarly, the derivative also should match. So the matching of this derivative and so these are the conditions for a well defined wave function. So at 0, the wave function should match and their derivative should match. Now we come to the next boundary condition. So this is one set of boundary condition. So equation 1, equation 2. Another set of boundary conditions come from the periodicity. So for the periodicity, so there is a theorem called Bloch's theorem, and Bloch's theorem says that if you have a potential with a periodicity A, then if you translate the wave function by the periodicity, then you will acquire a phase of e to the power I k a. So this is the statement of the Bloch theorem. So now if we want to do, so we'll look at the point. So we want to impose a boundary condition. So what is the boundary condition we are trying to impose? We are saying that, okay, you see that one period is from 0 to a, right? And we want to associate this particular psi of minus b, this particular at this point whatever is the wave function should be same as the wave function at here, at a minus b, right? So what we are doing is, so psi v of minus b, psi v is minus b is here, that should be equal to the value of wave function at a minus b. Okay, so it is exponential psi naught of a minus b with this phase term. Why this phase term is coming? It is coming because from minus b to a minus b you are translating by a distance of a. Okay, so I hope this point is clear. So So this
IKA
statement,
coming, sir?
huh?
How this IKA coming? IKA in
Oh,
the
how
previous
is this
also you were
IKA
putting
coming?
X.
Okay, okay, okay. Yeah.
Yeah.
So what is happening is, uh, so it is just a statement from, it is just a statement from this only. See, if you translate psi of x plus a, it is, so for example, what you are doing here is, what is psi v minus b? Psi v minus b is, uh, at you look at this point, you are coming from this side, approaching from the region where the potential is v, so this v stands for that, so you have the potential v, and you are evaluating it at minus b, so you are approaching the wave function from this side. Okay, now we want to, and this should match with the wave function which is coming from this side, isn't it? So the wave function which is coming from the left hand side of minus b is same as the wave function which is coming from left hand side of a minus b, right? That part is clear now?
Yeah. A based on A and B, I can understand. Yes.
Yeah. So psi
But
v,
IK, where
hold on,
the
hold on.
IK is taken?
I'll just tell you. This part is clear, no? So what we are doing
Yes.
is, we are
Psi
looking at
V
minus
and
b.
yeah.
See, we are looking at minus b position. At minus b, psi v of minus b, it stands for this. Psi naught of minus b, it stands for this. So the wave function has to be continuous at this point. That's what we are meaning. Understood?
Yes.
Now this part is, so how is this part related to this part? It is related by the Bloch's theorem. Okay. Now psi naught minus b is equal to, so this you can think of it as psi naught of a minus b minus a, right?
A minus B minus A. Yeah.
Okay, no?
Then it
So,
is nothing but B minus B. Yeah. Okay.
huh?
Yeah, nothing but minus B. Yeah. Got it.
Yeah, so this a minus a, I just took it. Now
You
you
have
can
added
think
A
of
and
it
then
as a
subtracted A.
minus b plus of minus a. This I can write.
Yes. A minus B is
So I just put a bracket only, just nothing. So it was like,
understood. Understood. Yes.
huh?
Yes. Yes, sir. Understood.
You got it?
Yes, sir. I got it. Yeah. A minus B plus minus A. Yeah.
Plus minus a. Now what I am doing is, now you see this equation. You put, you assume x is a minus b, and x is a minus b, and here your a is minus a.
Plus A. Okay. Yeah. Plus A is nothing but minus A. Okay. Got it.
Yeah.
Yeah.
In place of plus a, you replaces minus a. In place of x, you replaces a minus b. So what will happen if a is your minus a? So it should have been exponential e to the power minus I k a minus I k
Yes.
a, and x you are replacing with a minus b. So that is
Yes.
psi naught of a minus b. Clear?
Got it.
Yeah.
Got
So
it, sir.
that is what it is. And
Okay. So this step is skipped. So it's for maybe since you have already practiced it, this. Since this step is skipped, I could not immediately appreciate it.
yeah, okay. Yeah, so that may be a thing. It is good to have like go through this part once, so that it would
Yes,
be
sir. Yeah.
beneficial for you. Okay. So since this part is clear, the next part is just the derivative of that. So the derivative of the wave function from this side is same as the derivative from, so it is just, this is just a constant. you have to take the derivative of the wave function. Okay, so we have four equations: equation 1, equation 2, equation 3, and equation 4. And we know what is psi of v and psi of 0. So we have four equations, and this e to the power minus ika, that comes from the Bloch's theorem. Okay, and we know that psi naught x is a e to the power I beta x, and you take the derivative of that. If you take the derivative of this with respect to x, you just I beta will come here, and so this is just a simple derivative, right? And psi v x is c e to the power alpha x d minus alpha d e to the power minus alpha x, and here you are just taking the derivative of this expression. Now what we are doing is, we have to put these values instead of x, psi naught and psi v, we have to put the values x and x equal to 0, x equal to 0, x then x equal to minus b, a minus b, that we are going to put. So when you substitute for these values, so psi naught is there, derivative of psi naught is there, psi v is there, derivative of psi v is there. So equation 1 will give, so now you just, so these are just the steps. Maybe you go to room, in your room you can follow, like in your free time you can just go through this maths. So when you put the value 0, you will get this relationship among the constants. So a plus b is equal to c plus d. And when you, from the second equation means this equation, and you put 0 in these derivatives. So this derivative is here, put 0 here, so it is I beta a minus b, and so if you just put that, what you will get is this I beta a minus b plus alpha c minus d. And similarly from the third equation you will get this expression, and the fourth equation you will get this expression. So now you see, these four equations are the linear expressions in a, b, c and d. Okay, so what you can write this as, this a, b, c and d, you can write, for example, I will just give one example. This a, b, c, d you can write as a plus b minus plus minus 1 c plus minus 1 d is equal to 0, right? This you can write as I beta a plus minus I beta b plus minus alpha c plus alpha d equal to 0. So this is equation 1, equation 2. Similarly here also you can write some expression time a plus some expression time b plus some expression, you can rearrange this third equation, plus some expression time d, so this you will get third. Similarly here also you can rearrange this equation as some expression time a plus something times b plus c plus d is equal to 0. So these are the set of four equations, and you have this a, b, c and d. It is a linear combination of a, b, c and d. You have four equations and four variables. So since there are four equations and four variables, and it is a system of linear equations, you can, so this system of equation will have a solution when the determinant of its coefficients is equal to 0. So this is a statement from linear algebra. So here I am just writing the coefficients here, a, b, c and d. So a, b, c and d, and these are just the coefficients. See, remember from equation 1 it was 1 times a, 1 times b, minus 1 times c, minus 1 times t. So that is what it was here, 1 times a, 1 times b, minus 1 times c, minus 1 times t. Similarly I am writing all other coefficients. Now our task is to find what is the determinant of this, and that determinant has to be equated to 0. Then only this system of linear equation will have a solution. So before doing that, so this is a 4x4 matrix, it is a very big matrix, so we need some simplification, and to do that simplification there are some mathematical steps. I will just brush over that. You can and like I have solved it for you, you may just go through it, or it is okay if you don't go through it also. What is important for us to understand, that this we are getting for that periodic potential, and we'll try to see what are the consequences of this. So just for the sake of completeness, I will go through the mathematical steps. So the C1, so we are saying that this column is C1, this column is C2, this column is C3, and this column is C4. If So what we are first so this is again a statement from linear algebra, that if you subtract for example, if you do this operation, replace the column C1 by C1 minus C2. Okay, so what I am doing, I am replacing this with C1 minus C2, means I will subtract this from this. So 1 minus 1 is 0. So I beta minus I beta is 2 I beta. So that's what I have used. So 1 minus 1 is 0, I beta minus 8 is 2 I beta. So I have done this operation. This is called a column operation. Okay, and so once we do this column operation, we will get this. Similarly, we do two more column operations. C4 we will replace with C4 minus C3. So here we get 0 to alpha minus 2 sine hyperbolic alpha beta. So here I have used one thing, this might be helpful for you, that e to the power I x is nothing but sorry, do you know this thing, equal to e to the power ix plus e to the power minus ix by 2. Like, are you aware of
Somewhere
this?
I have seen this, sir.
Yeah.
Yes, I
So,
have
so
seen
that's
this.
what I have used here. For example, here this sine beta, how it came up. So e to the power minus ika, if I subtract this, if I subtract this from this, then what will I have? E to the power minus ika, and this will be common, e to the power minus I beta a minus b minus e to the power minus I beta a minus b.
Correct.
So what I am doing is basically this. So I'll just write some expression, it will be helpful if so
Sure, sir. So sin x will be
so sin x is nothing but your e to the power ix minus e to the power minus ix by 2I. Okay, and then what else is there? Then cos hyperbolic x is e to the power x plus e to the power minus x by 2, and that is called sin hyperbolic x is e to the power x minus e to the power minus x by 2. Okay, or in other words, what you can write as so these are the expression. Suppose if you have e to the power ix minus e to the power minus ix.
so in the cos x also there is no 2i. Cos x is e
Cos
power
x
ix
only 2.
plus only 2.
Yeah.
Only 2i comes only in the sin x and not in any of the hyperbolic also.
Yeah. So if you have this e to the power ix minus e to the power minus ix, that you can write as 2i. So I just took this 2i to the left hand side, 2i sin x.
Yes.
It is just a mathematical trick that will be useful for you to do some simplification. So, and e to the power minus ix, if this plus comes, this you can write as 2 cos x. Similarly, e to the power x plus e to the power minus x, you can write as 2 cos hyperbolic x. Similarly for this. Okay, similarly, so that's how I got this sin hyperbolic, cos hyperbolic, all these things. Okay, so that we got by doing this C4, this column operation, C4 replaced by C4 minus C3. Then one more column operation we have to do, C3 replaced by C2 plus C3, and from there you will get this expression. So the point of doing this was, so this is the entire matrix. So this matrix now it can be evaluated for its determinant, and the purpose of this column operations, we did 3 column operations here to get zeros in these rows. So now the determinant of this matrix is just this these times the cofactor of this particular element. So you know to get the determinant, right, in by that 3 by 3 matrices.
Yes, 3 by 3, yes.
Yeah. So what we do, we take the first element, then take the determinant of this, then minus of second element, take leave out this row and column, then determinant of this, right? So similarly here also we do the a12 is this, and cofactor of 1 2 that will evaluate in the next thing. So this is what we did. Then what we are doing, So this we are determining the cofactor of that element. So what we did was we left out this and this row and this column, and taking these terms 2 I beta minus I beta alpha, and so these three columns we are taking and equating it with 0. Okay, now you see, so this is this left hand side is the determinant of that 4 by 4 matrix. Okay, but you see that we have to equate it with 0. What we can do is you can take out some common common factors. For example, you see 2 2 2, here also 2. So what you can take out, you can take out a factor from an entire column. So this 2 you can take it out. If this is also minus 1 to the power 1 plus 2 is 3, this also it can be dumped to 0, this also can be dumped to 0. So you are left with this expression. Now we can do another column expression, column operation to make this quantity 0, because here see minus I beta is there, minus alpha is there. So we can replace this column with the C2 plus C1 plus C3. So what we are doing is, this is the expression we had, and we will do C2 plus C1 plus C3, and we will see that once we do that, for the first row at least we can see that it is becoming 0, and we will calculate what is the term we will get for this and what will be the term we will get for this. So term M22 and M32. So that also I have evaluated. So we will get these two terms, this term and this term, and when you just put that, you will get this particular matrix. And when you expand this matrix, you will get this big expression. Okay, and once you get that expression, you can do further simplification. You will be left with, so these are the simplification steps. Okay, you can go through it, and finally what you get is this. After all this simplification, the one which is the one so finally what you get is this particular expression. Okay, here is one small mistake. Yeah, so this is what you get after all the simplifications. Okay, here also.
Sir, can I go to the previous slide? Cos k.
Huh?
The last expression.
Yeah, this is the same expression.
Ah, okay.
Yeah.
Cos beta e minus b.
So after all this mathematics, what you got is this. So this Ka, this, where was this K first introduced? This was introduced in that Bloch theorem, which tells you about the periodicity. And the periodicity, it is a property of the crystal lattice, right? And this so it is related to the wave vector of the nearly free electrons. So this K, it tells about, so this is that K vector of the electron waves which gets diffracted when it comes to the order of the, when the wavelength corresponding it comes to the order of that periodicity. On the right hand side, what we have is, on the right hand side we have an expression where the unknown variables are alpha, beta, A and B. See, this A and B are fixed once we fix the potential, because A and B are the dimension of that well, dimension and the periodicity of the well. So it has to do with the geometry of that potential. So we cannot much do anything about A and B, they are fixed. But this alpha and beta, they are related to the energy of the, alpha and beta are related to the energy of the system. So you cannot vary alpha and beta independently, rather what you can vary is the energy E of alpha and beta. So when you vary the energy E, like you sweep along energy E, alpha and beta can take some values. Okay, now you see this expression, cos Ka is a sinusoidal function and it has value only from -1 to 1. But the right hand side, it can take values depending on what the alpha and beta are, it can take values which can be more than 1, which can also be more than 1 and less than -1. Okay, so what you will get is, so
A and B are the what it says, sir, that the particular location.
A and B,
Periodic of the periodic.
A
A and
and
B
B
are
are
the
the
geometry of
dimension.
the
Huh?
A and B are the geometry of the periodic function, is it?
Yeah. So these are the geometry of the periodic function. So once you fix the periodicity of the potential, you cannot change it. What you can change is, you can look for what are the different allowed energies of the electrons that you can ask. So for different energies, how does this look like? So to just draw some rough schematic. So what the right hand side, see, the cos Ka can be between -1 and 1 only. But the right hand side, how it looks like is, it looks something like this. It looks something like this. And
How
-1
did
to,
you arrive at 5 electron volts, sir?
no, this I just took an example just to, so I will show you one thing. So what will happen if we plot the right hand side? That's the question we want to ask. So here also I made a mistake. So the left hand side has to be equal to right hand side. And the, what is the parameter for the right hand side? The parameter for the right hand side is that energy. A and B are fixed, some fixed value we are taking. Okay. And what we are doing is, if we just plot that, so for the parameters which are listed on see,
It's attenuation, is it? Sinusoidal attenuation.
so this is the, okay, this doesn't look so promising. Hold on.
So a wave with attenuation, correct?
Yeah, it is a wave with attenuation, but the point to note here is that, what I want to say is, this cos Ka, it has a value from -1 to 1, right? This you are clear, right? Cos Ka has to be between -1 to 1. But this can
Yeah.
take
The value of
values,
0.
this expression can take value from, it can be more than -1 to 1. So it is like this, the plot which I have plotted here. Maybe I will make a new diagram, new slide. So how it will look like is, suppose if you have, so this I am plotting the right hand side, huh? So the right hand side will look something like this. Okay, it is just going to attenuate, but this is your right hand side, RHS value, and with respect to energy is on x-axis, and this is your right hand side of expression. But this only makes sense when this value is between -1 to 1. If this is 1 and this is -1, then only in these regions are you getting me what is happening? So only in this region, so for example, these values are the physically relevant values, because it is between here only it can be satisfied. There is some value of K for which LHS can be equal to RHS. LHS equal to cos Ka, and cos Ka can be between -1 to 1 only, right? So only those values which is between -1 to 1, that has only the real values. So those are the allowed values. You are getting the point?
Yes, sir. Yeah.
Yeah. So now see, till here the RHS is between 0 to 1, something like that. So these are allowed. But once it goes beyond 1, these are not allowed, because cos Ka cannot be more than 1. So again, so this is a
Yes.
forbidden region, forbidden value. So from here again it comes into less than -1 to 1. So this is again some allowed values. So these are your allowed energy range. For this you can find some. So these are the values. So you are, what you are doing, you are sweeping with energy, changing the alpha and beta, and you are getting this. So, and those values of energy for which the right hand side is between -1 to 1 is your allowed values. You are getting right what is happening. So the blue color
Yes,
bands
sir. It's
that I
very
am
clear.
drawing,
Yeah.
in those
These
regions,
are all allowed.
these are allowed.
Yeah.
And so why they are allowed? Because that's where the left hand side can be equal to your left hand side. So these are your energy bands. So you see, right, like how we are getting this energy bands. Okay, yeah. So that's, and so I hope this explanation is clear. So what we have is, so just since cos Ka is between -1 to 1, since cos Ka is between -1 to 1, just hold on, and RHS is this thing. So RHS can take values, RHS can take any values even beyond -1 to 1 based on the values of energy. But the allowed values are those for those values of energy E for which the right hand side belongs to -1 to 1. This point is clear, right?
Yeah, this is clear, sir. Clear.
Yeah. And the forbidden energy values are those for which the energy, the right hand side is not in 1 minus 1. Okay. So not in 1 minus 1 is, this is not in -1 to 1. So this is a forbidden energy. Okay. So a window in the right hand side is forbidden to the system, and to the corresponding values of energy being okay, what it is, yeah. So that's what the forbidden energy is, the region in which the right hand side is not between -1 to 1. That's all. So with this what we got is, for a periodic potential we saw, and for a periodic potential we quantitatively saw the formation of energy bands. So now what we are going to see, so this we had seen
Sir,
in the,
can you go back to the previous slide?
yeah,
Can you go back to the previous? Just I want to note down that equation.
this equation you want to know now. Yeah.
No, the previous one, the one which you showed now. The next one. Next
There
slide.
is no equation here, no?
This one, this one.
Oh, this is the right hand side of this expression.
Yeah, so that one, I was just writing down what are the forbidden and accepted values.
Oh, okay. Sure.
Yeah. RHS can take values. RHS can take a value. Or -1, based on values of E. Based on values of E. Allowed energy values are those values of E for which RHS is. What is this symbol, sir? RHS, you put
So
one epsilon.
epsilon is actually, in set theory it is called belongs to. This is a particular set of values -1 to 1. RHS belongs to -1 to 1. Or you can just write, okay, I mean, yeah, RHS belong, and this, it means it, this slash means difference. So R is the real line minus the real set of all real numbers except the numbers from -1 to 1, including -1 and 1.
Okay. Yeah, this is new to me. Okay, sir.
Okay. Okay, so this we had seen in the last class, and what we had seen that there would be some energy gap arising here, and the bands will be, so this is in the k space or the momentum space that we are talking about, and this is that value, that k, just now we saw that cos ka was there, right? It is that k, and these are your uh, so in the previous plot these were drawn vertically, right? The energy axis was on x axis, so this is
Yeah.
another representation of the same thing in the k space. Here we are plotting energy in the right hand, in the y axis, and this is your
Yeah.
allowed band, and these are your forbidden band, or uh, so this is the forbidden energy, this is your allowed band, and the gap between this is called a band gap. Okay, so we'll come to that in a while. So what we have uh, done till now is what we have done till now is we have seen, we solved the Schrodinger equation, and then we obtained the band gap. Okay, but all this while we had in the back of our mind we had that electrons are free. So till now what we have done, initially we started our discussions like from, if we look from the very beginning, we say that okay, we have a metal have free electrons, those free electrons, then we impose the Pauli exclusion principle, we determine the specific electronic heat capacity and so on. Then we
Yeah.
told that okay, electrons now will see the crystal structure. When electrons will see the crystal structure, anisotropy and all this, anisotropy will come into play, diffraction will happen. We saw about
Yeah.
different crystal like BCC, FCC. Then we are saying that, so all this while we had, so we are developing upon the free electron model. So when we are talking about the free electron theory, we are saying that okay, we have a solid in which the constituent atoms are giving out their valency electrons, and these valency electrons can roam around freely in that, in the volume of that metal. Now we will be saying that, now we'll be understanding something called a tight binding approximation. So in tight binding approximation, it is a different approach. Why different approach? We will come in a while. So till now, what we have is this. So we got this parabolic curve was for. Uh, so this parabolic curve was for the.
ఆయన నేను చూసి ఎందుకు త్వరగా నొప్పి అని
Uh, Yeah. So this parabolic curve was for the free electrons. Then when we introduced the lattice, we got these band gaps. Okay. And we are saying that the band gap, it is denoted as Eg. And based on this, what we can talk about is we can classify different material in as semiconductors and insulator. Okay, now these are the energy bands, and we had told that, if you remember, that these are actually not a continuous parabola. And if you remember that class, what we had discussed was this. We had discussed that these are very closely spaced. So you remember this expression, k equal to n pi
Yes.
over a and k equal to n pi over l. So this is n,
Yes.
this is pi by a, and
For large number of
there are
L.
very closely spaced. So these are discrete points. Okay, discrete but very closely spaced. Now if you try to levels, yeah, now if you try to draw the energy levels here, for example in this band, so this is actually very closely spaced, very closely spaced, like for example here, if I want to zoom this here, this is not a continuous band, it is very closely spaced, uh, very closely spaced energy levels. Okay, That's how you have to think of it. And then you have a suddenly very big gap, and then you have very closely spaced energy levels. These energy levels can be filled by electrons. So now what you have is, if you have this, so when I am drawing this big energy, this blue color energy band, it means that it has these are very closely spaced energy levels, and all of these are filled. And the next band, these also have a lot of states, but these are not filled. So these are also closely spaced states but not filled. Now if this band gap is more than 2 electron volt, then we will call it an insulator. And if so this we are talking about only two uppermost bands. The second highest band is your called valency band, and the one immediately above that is called conduction band. Now if the distance between this distance means energy gap between these two bands is more than 2 electron volt, we will call it an insulator. If it is less than 2 electron volt, we will call it a semiconductor. And there will be some systems in which the valency band is totally filled, but there are more electrons to it, so those electrons will occupy some of the energy levels in the conduction band as well. So now for these electrons, for example, here let's say these electrons at this energy gap, they have an energy level which is empty just immediately next to it, right? And very closely spaced. Like for these for electrons in insulator and semiconductor, the next energy level is like they have to make a jump of 2 electron volts, about 2 electron volt. But here, without any such big energy jump, they can easily get excited to the next energy levels. This is the case of a metal, where one of the band is half filled or incompletely filled. There can also be situation in which one band is overlapping with the other band. So this is one band, that band is overlapping with another band. So the energy, so these electrons which are here, without too much of energy loss, they can just go to the conduction band and they can be free. So in terms of band, these are called metals. Okay. So now we have talked about something called Fermi energy, and Fermi energy we have told that it is the highest occupied energy level. For example, in the case of a metal, the highest occupied energy level is what? The highest occupied energy level is here, EF. So this will be EF.
EF. That's
Here
a Fermi
also
level, yeah.
EF, right? But in case of insulator and semiconductor, the highest occupied energy level is where? The highest occupied energy level is here. But by
Yes.
convention, what we take is the Fermi energy we take as the middle of the conduction band and valency band. So somewhere here.
Okay.
So that is your convention. So here the blue line, it represents your Fermi level for conductor or insulator, and this is a convention. Okay. So that's how we classify metals, insulator and semiconductor in terms of the band. Okay. In terms of energy bands. Okay. So till now the approach has been, we have been looking into the free electron approximation, where we say that okay, the solid already exists and each of the atoms are giving out the free electrons, and those free electrons are responsible for the metallic behavior of the material. The electronic and thermal properties of that material. But there is another approach, it is called the tight binding approximation. In tight binding approximation, what we will say is, we have individual atoms. Individual atoms will have individual energy levels, and then we will bring the atoms close slowly to make a solid, and then we will see how this solid formation takes place and how the band will form. So one thing to note is that this free electron approximation, it is well suitable for metals, but for semiconductors and insulators, tight binding approximation is more appropriate. Okay. So let us look at, so what we are doing in tight binding approximation, we will be looking at an individual atom. So imagine, let's say we have 100 atoms and all of them are very far away from each other, they are not interacting with each other at all. Then if you take one of those atoms, it will have certain energy levels based on its atomic structure, right? Now we want to bring all those 100 atoms together and make it into a crystal. Then we will see how these energy levels will get modified. So one of the important thing we have learnt is that the electron are fermions and they follow something called this Pauli exclusion principle, which means that no two electrons will have the same quantum numbers, or two electrons cannot occupy the same quantum state or the same energy state. So what will happen if we bring two atoms very close to each other, then their electron cloud will start overlapping. Now since the the electrons cannot have the same energy levels, this energy level will start to split. And for example, one electron, so if you bring in two atoms, then this energy level will split to, E3 will split to two closely spaced energy level. For example, like this. If you are bringing close two atoms close to each other, then you have E1, E2, E3. If you bring them close together, it will split into two, like this. If you bring three atoms, it will be 1, 2, 3. This will be very, very closely spaced, okay? Very closely spaced. 1, 2, 3, 1, 2, 3. Now imagine if you have, like when you make a solid, it is of the order of Avogadro number of atoms. So then what will happen is, you will have this number of energy levels for a particular level. Let's say this is E3 band. It will have Avogadro number of these closely spaced energy levels. You are getting this, right? How this band is forming? This is how it is forming.
Yeah.
It will have Avogadros of the order of Avogadro. This is also will have of the order of Avogadro numbers. This is how this is the qualitative picture of how the band formation will take place when you bring in lot of atoms together. So this is an important diagram. So what we are saying with respect to the interatomic separation, how does the band formation, or how does the band structure will change? So when you are when all the atoms, let's say you have 1000, or like let's say you have 100 atoms, when all of them are far apart, then you have, so we look at three energy levels, E1, E2 and E3. So here I have interchanged, but it is, so even the E1, E2 and E3, okay? When you bring them closer, so at a certain point of time, so E3 is your highest energy level, so, or the outermost orbital. So first the outermost, so when you bring in two atoms close together, first the outermost electron cloud will overlap. When they will overlap, it will start getting splitted. Why it will get splitted? Because of the Pauli exclusion principle. And it will get splitted into 1000 different, like if you are taking 1000 atoms, it will be getting splitted into 1000 different energy levels. So here, for the sake of drawing, it doesn't look very nice and neat, but you can imagine it 1000 of these branches coming. Then if you bring in further more close at certain point of time, so the outermost orbitals are already there in they are interacting. Now the inner, little bit inner keep this thing. Yeah. Just this is 2 and this is 1. Yeah. Now what is happening is, so outermost orbitals are already, they have already started interacting. When you go a little bit closer, when you are coming further more close, then the inner orbital also start interacting. So when the inner orbital will start interacting, it will start to split into band, right? Then when you bring further more close, then what will happen? Then the further inner orbital will start getting splitted. So this is how your band will start forming. Now this, so what is this interatomic spacing? So there would be an equilibrium interatomic spacing, and based upon that equilibrium spacing, you will have the band. For example, let us say this blue line, if your equilibrium spacing is this blue line, then corresponding to this, what is the band? So the outermost band, it will look like, so this is the energy, so this is the splitting of energy level E3. So this is the E3 band. This has not yet splitted, this is just a single line. This has not yet splitted, this is just a single line. So this is your band structure for this system when your equilibrium spacing is x1. If your equilibrium spacing is x2, you see the first band, the outermost band, it has been created and it is like this big. You are able to follow, right? This green, this is what the outermost band is. Then just lower band is this one. So you have to take what is overlapping here at this spacing. That is your band here, and this has not yet started to split at this spacing. So this is your other band. So this is how, when you bring in atoms close together, you will start formation of band. So this is what x1, x2, these are interatomic spacing. Now you see what would be the band gap here. The band gap, when the equilibrium spacing is x1, the band gap is from this point to this point. But when you bring further close together, if you reduce the interatomic spacing, you will approach the green band. So the green one, you see that band gap is starting to decrease. You are able to see this, right? The band gap is decreasing when your interatomic separation is decreasing. So if you compress a solid and you try to somehow reduce that interatomic separation, your band gap will start to decrease. Okay, so this is what we understand from here. Now what will happen if the material is subjected to very high pressure? So on the x-axis we have pressure, and here we have energy level, and we are talking about two. So here we have, this is one band at atmospheric pressure, and this is another band, and this is your energy band gap. But as you start to apply higher and higher pressure, so if you apply higher pressure, what will happen? The interatomic separation will start to decrease, and if that will decrease, your band gap will increase. Band gap will decrease, and these bands will start increasing. The band will start getting wider. Okay. So that is what it is happening. The bands are getting wider as you increase the pressure, the interatomic spacing will start to decrease, and these bands are becoming more and more wider, and the gap between these bands is decreasing. Now we had the definition that if the band gap is more than 2 electron volt, then it is an insulator. If the band is less than 2 electron volt, the band gap is less than 2 electron volt, it is a semiconductor. And if they are overlapping, then it is a metal, right? So now if you see this band gap from here to this point P1, this pressure P1, the band gap is more than 2 electron volt. So this is the region of when the metal is when the material is an insulator. If you apply some more pressure, then what will happen? Then this band gap will reduce to less than 2 electron volt. So that is the region of your semiconductor. And if you still increase the pressure and till the point that the bands start overlapping, then it is in the material is in the metallic state. Okay. So this is how your material will behave if you subject it to high pressure. But we have to keep in mind that this pressure, the range of pressure, it is of the order of 10 to the power 6 atmosphere. So it is not that sensitive to pressure, because it is very difficult to create 10 to the power 6 atmosphere. This can happen if you are making a semiconductor device or like some device here in Earth, sending to some other planet or some other system, some other region where your pressure is like orders of magnitude more than your you send to Jupiter, let's say, there the pressure is very very high, and there your semiconductor devices that you send from Earth, you might be thinking it is an insulator, there it might be behaving as a metal or a semiconductor. So pressure has an effect in the material properties. Okay, so that's what you have to keep in mind. Okay, this part is clear, no?
Yes, sir. This is very clear.
Yeah. So we'll talk about the semiconductors. So semiconductors are of two types. So semiconductor, we know that the band gap is less than 2 electron volt and the valency band is totally filled, conduction band is empty, and the band gap is less than 2 electron volt. So there are two type of semiconductors. One is called intrinsic semiconductor and other is called extrinsic semiconductor. In the extrinsic semiconductor, we add some kind of impurity to it, some particularly designed impurity to it. But in intrinsic semiconductor, it is a pure element or a pure compound. So the elemental semiconductors are silicon and germanium. These are like group 4A elements in the periodic table. And so group 4A elements, and there are other type of covalently bonded other type of elements as well, other type of compound semiconductors. For example, gallium arsenide. Gallium is a group 3 element and arsenide is group 5 element. So this type of semiconductors are called 3-5 semiconductors. So where one of them is from group 3 and other is from group 5. Similarly, 2,6 compounds can, for example, cadmium sulfide. This is a 2,6 compound. So this is also a semiconductor. And what we can keep in mind that as you increase this, like for example 3,5 to 2,6, so this is a bit more ionic. So all of them are covalently bonded, but this is a bit more ionic bonded, ionic component to it than this. Ionic means there would be a kind of charge separation. For example, you cannot have 1,7. For example, sodium chloride is a 1,7 compound, but it is not a semiconductor. Why? Because the electron from sodium will be completely transferred to the chlorine atom. So it will be an ionic bond instead of a covalent bond. And for you to have a semiconductor, you need to have that covalent bond in it. Okay, so this is about the intrinsic semiconductors, and these are some examples. In extrinsic semiconductor, what we have is we put some kind of impurity. For example, if you have a silicon and you dope it with, for example, arsenic is a group 5 element. If you dope it with a group 5 element, you get something called an N-type semiconductor, where your majority charge carriers are electrons. On the other hand, what you can do is you can dope the silicon with a P-type with a group 3 element. When you do that doping, what you have is you will have a p-type semiconductor, and there your holes will be there are something called holes. Holes will be your majority charge carrier. Now what are holes? Holes are, for example, if you have so this is your valency band and this is your conduction band. So when one electron is excited to the conduction band, there will be one energy level which will be devoid of electrons. That that absence of electron is called hole. Okay. So in p-type semiconductors, the majority charge carriers are holes, and n-type semiconductor majority charge carriers are electrons. So we know this. We know that conductivity is J is equal to sigma E, where sigma is your conductivity, E is electric field, and J is your current density. And from Drude model we had learnt that it is NeVd. Vd is your drift velocity, N is the number density of electrons, and E is your electronic charge. And so from here sigma is equal to NeVd over E. So I just took this to right hand side. This Vd upon E, this quantity is called mobility, that we write it as mu. Okay. And for intrinsic semiconductors, for every electrons in the conduction bands, there is a hole in the valency band, and the conductivity is given by, so there are two spaces, one is electron and other is holes. The charge of an electron, the magnitude of charge of an electron is same as the magnitude of charge of a hole, and mu E and mu H are the mobilities of these two, the holes and electrons, the electrons and holes, and N is the number density of electron, P is the number density of holes at a particular given temperature. So in an intrinsic semiconductor, what we have is the number density of electron is same as the number density of holes, and that is denoted as Ni. So you just put sigma is equal to Nie, and this mu E and mu H are just like, what we did was N we replace it with Ni, P we replace it with Ni, and we took Ni times E as common, and what we have in bracket is mu E plus mu H. So that's what we have. So this is about the intrinsic semiconductors. So now what happens on doping is that,
go back to the, sorry, just go back to the previous slide.
yeah,
P is the holes, right? Okay.
P is the number density of holes.
Number density of holes. Just writing down.
Yeah.
So for intrinsic, it is N equal to P equal to Ni. Ni is the carrier concentration.
Yeah. N is the number density of electrons.
No, Ni is the intrinsic carrier
concentration. Yeah.
Which makes it sigma is equal to Ni of E mu E plus mu holes. Okay. Okay.
Yeah. So what we have is intrinsic semiconductors. So this is the picture we have. In semiconductor, by convention we take that the Fermi energy as the center of conduction band and valency band. The valency band is filled and conduction band is empty. Now when you put the so extrinsic semiconductors, you put in some impurities. The impurity can be n-type impurity. N-type impurity means you put group 5 elements as dopant, and p-type impurity, okay, so you put group 5 elements as dopant, right? Then what will happen is, so the impurity state is this dotted lines. So here are your electrons, so there will be some extra electrons. those electrons will be your majority charge carriers. So this dotted line that you see, that is your impurity energy level. So up to this it is filled with the electrons of the semiconductor itself. Okay, now the electrons from that n type dopant, they will occupy this energy level. This is your topmost energy level. Now it is easy for these electrons to jump to the conduction band. Rather than from here to here, they can easily jump from here to here, and the Fermi energy, it is somewhat, it is between this energy level and the impurity energy level and the conduction band. So the Fermi energy is between where, so it has gone towards the conduction band in n type semiconductor. This is clear what is happening. So the point to remember is that so here,
Yes, sir. This is clear.
yeah, n type impurities are, n type dopants are group 5 elements. Group 5 means, so it will have one extra electron, 4 plus 1. Okay, and these are doped with group 3 elements. So 3 equal to 4, so one electron less. So what will happen is, in p type semiconductors, so there will be an energy state created here at this level, acceptor level, where there would be empty, so these are empty states. An empty state will be created here. So now it is easier for the electrons to jump from here to this here to this acceptor level. So this energy state is created because of the impurity, because of the p type impurity. Okay, and your Fermi level, that will come towards your valency band. So this is your EF now in the p type semiconductor. So this is how your Fermi energy changes when you do the doping. So what you have to remember is, in n type the Fermi energy is near the conduction band, in p type the Fermi energy is near the valence band. That's all. Okay, so now what we'll do is, we'll look into how the,
Sir, group three, when we say,
yeah,
do we say n type is doped with 5A?
n type is 5a,
Whereas group 3, anything that you said, 3 equal to 4 minutes.
yeah. So what I mean is, here see, for example, uh, group 3 is so this group has silicon. So maybe I'll show you a periodic table. Oh, you're able to see this, right? Yeah, you see this. This is your group 4. Okay, silicon, germanium. So this is your group 4 region, group 4 elements. This is your group 3a elements, okay, and these are your group 5 elements. Now like if you know the periodic table, so outermost cell of this will have, so outermost cell of group 4 elements will have 4 electrons, and outermost cell of group 3 elements will have 3 electrons, and outermost cell of group 5 elements will have 5 electrons. And in semiconductors, what happens, they will have to do a covalent bonding. So when you put some of the impurity from group 5 elements, then what will happen, so let us take silicon, and you are putting some impurity, let's say arsenic impurity. So what will happen, 4 of these electrons will bond with 4 of arsenic electrons, and there will be one outermost electron of arsenic left. So that one extra electron will contribute, that is your extra electron, that electron will contribute to the conductivity of that material. So that electron, that extra electron will have the energy level somewhere here. You understood, right, what is happening?
Yes, sir. Yeah.
Now see, now what will happen, for group 5 elements, so if you do, let us say you have silicon, and you put the impurity, gallium impurity, let's say. So gallium has 3 electrons, silicon has 4 electrons. So 3 of these 3 of the silicon electrons will bond with 3 of gallium electrons. Okay, there will be one more bond of silicon where that single electron is extra, but it has no, there will be an absence of electron from gallium. You understood this part, what is happening?
Yes, sir. Yeah. Clear.
Yeah. So what is happening? There will be 4 bonds, but one of that bond will have absence of 1 electron, because gallium has 3 electrons only. Okay, now. So that absence of electron, that will create an energy state. That energy state is that absence of electron. It will have that absence of electrons will create an energy state somewhere at here, this level. Now what will happen, since these are very close to the valency band, it is easier for the electrons to hop into these levels. Now you imagine, now if you give some temperature, then that by taking that energy from that thermal, by taking that thermal energy, the electrons can hop from these levels to the level which is just immediately above them. So what will happen is, if you increase the temperature, so at low temperature, at very low temperature, the electrons cannot hop out. For example, let us first talk about, so this is your this is totally filled, this is your intrinsic semiconductor, okay, this is your Fermi energy. So I'm not drawing the Fermi energy. So this is your, if it is your n-type semiconductor, where will be the where will be the donor level? N-type is extrinsic, okay. The energy level will be somewhere here, impurity energy level. And if it is your p-type, the next energy level will be somewhere here. This is for p-type. Now what we are doing is, we are trying to increase the temperature. So we want to increase the temperature. So when we increase the temperature, what will happen? So at very low temperature, all the electrons are freezed in their ground state. Okay. So I don't know if you remember so here this is energy, okay, E, and we had this thing F of E. This is the occupation probability, EF. You remember this function?
Yes, sir. Yeah.
Yeah. So now if I try to plot that here, so for example, for this the Fermi energy somewhere here, for here the Fermi energy somewhere here. Huh. So now if I try to plot that here, and this is your F of E, let's say. So it will come like this, probability of occupancy is 1, which is clear that it is totally 100% occupied, and it will drop here at 0 temperature, and here the probability of occupancy is 0 and 1. So you understood this particular part, that but here also what will happen, okay, so this is your Fermi energy for this value EF, this is F of E, 0 1, and this. You are able to follow this diagram now, what it is going on here?
Yes, sir. Yeah.
0 1. Okay, now imagine that we are trying to increase the temperature. When we will increase the temperature, what will happen? This thing will get smeared, right? It will get smeared like this. If you remember this, when we increase the temperature, this smearing used to take place. This part is clear?
Yes, sir. Yeah.
Yeah.
With temperature it smears.
Yeah.
Yes.
So when the temperature is 0, you see, when temperature is 0, no electrons, so here this thing is occupied with 100%, this level is occupied with 100%, but the conduction band is not occupied. Similarly here also see, this is your EF, it is occupied till valency band, but the next immediate energy level is not occupied when your temperature is 0. But when you increase the temperature, so when you increase the temperature, then it will start to smear. You understood what will happen now? So when you start to smear, you see now there is a non-zero probability of this conduction band to have some electrons. Here also you see there are some non-zero probability for the conduction band to have some electrons. So in the extrinsic semiconductor, so when you increase the temperature, you will have the carrier concentration increasing. So this red, if you follow this red curve here, yeah, if you follow this, oh, yeah. So what is happening is, if you increase the temperature, then you will have some carriers in the immediately next band, and you will have your carrier concentration will increase till certain time. So it is increasing as you increase the temperature. But for the intrinsic semiconductor, you see it is not increasing. Even if you increase the temperature, increasing the temperature means you are smearing this occupation probability. Okay. So even after you are increasing, it is not changing much till the point when you are really changing it to very high value. So when you are really changing it to high value, let's say I will plot in this black glue. So at very high value it will be somewhat like this. So it will smear very nicely when you have a very high temperature, and then you will have the extrinsic semiconductor behaving similar as the intrinsic behavior, as an intrinsic uh, the extrinsic behavior will be same as the intrinsic behavior. So so you got why this thing is happening, no? Why we have very low carrier concentration here, then we have a plateau, and then we have a sudden increase. So basically we have three zones.
Yes, sir.
Yeah. So we have three zones in extrinsic semiconductor when we increase the temperature. So one is called freeze out zone, where when we are at very low temperature it is called freeze out zone. Then when you have some moderate temperature you have extrinsic behavior, and then you have intrinsic behavior. Whereas in intrinsic semiconductor you have only one region, and that is your intrinsic region. That's all. Okay, so that is your concept, how it varies with the temperature. So next is how does the mobility changes? So mobility is mobility, if you remember, it is related to the conductivity S and E mu. So if you have so the electron are more mobile than your holes, and if you increase the temperature, then your mobility will decrease. So that's what we had seen also in the Drude theory. But what happens is, if you increase the temperature, then the number density of electron will increase. And when the number density of electron will increase, but mu is decreasing, but number density is increasing. So the increase of number density is so much so that sigma will increase, the overall factor, overall this product will increase in spite of this mu decreasing. If you see this plot, the mu will decrease when you are increasing the temperature. So this is temperature on this axis. So even if mu is decreasing, because n is increasing when you increase the temperature, you will have an increase of the conductivity. So that's why with increase in doping or increase of temperature, n will increase so much so that it compensates for the decrease in mu. Okay, so that's all for how the electrical properties changes with temperature. Now we'll look at something called something about the electrical optical properties of the semiconductor. So we have this band gap, right, Eg. So electrons can take the energy from light and they can jump into the conduction band, and energy will be absorbed only when your incoming energy of the light is more than your band gap. So h nu is the energy of the photon. Only if it is more than the band gap, then absorption will take place, and if not, then the material will be transparent to that particular wavelength. Now we'll talk about a bit about anisotropy. So electrons will see different periodicity in different directions. So based on that periodicity, we'll have different. So for example, here along 110 in a let's say in a crystal, along 110 you have certain periodicity. Along 111 direction you have another periodicity. So this is your two bands, let's say, and these are your band along this 110 direction, and in the other direction if you plot, it looks something like this, let's say. In that case, if you plot the band, you see the next immediate band more than this is your this green color band. This type of bands are called indirect band gap semiconductors. If this were the shortest gap, then this would have been a direct band gap. But since there is something else coming in between this band in other direction, which is coming here, It is called an indirect band gap. And for optical properties, what we need is for this optical transition happen only when we have this electron. It doesn't have to change its direction. So if it changes the direction, we have to satisfy the conservation of momentum as well. Okay, so that is why the indirect band gap semiconductors are less efficient for optical properties. And if it is a direct band gap semiconductor, then it can be used for optical properties and optoelectronic devices. So for you to, the point to remember is that for optical devices, semiconductor optical devices like semiconductor laser or LEDs, what you need to have is a direct band gap semiconductor. Okay, so this is all about the concepts that will be required to solve today's question. So let us have a discussion of these questions. Okay, so a semiconductor based circuit might fail in spacecraft engineering entering a Jupiter due to, so what can happen?
High pressure.
High pressure, correct. So this is your correct answer. What about the next one? If the band gaps are considered at three levels at interatomic spacing x1, x2, x3, so you remember this plot, no? So I'll just
Yeah.
do this.
X1 less than x2 less than x3.
We had this plot, and we were doing something like this. So let me draw x1 here. So x1 is lesser, right? So x1, let's just draw here x1, x2, x3. Relative band gaps will be such that band gap at distance x2 will be wider than x1. Band gap at x2 is what? Band gap at x2
Wider.
is this. So this is 1 and this is 1. Band gap at x2 is this gap, okay? This is band gap at x1 and this is band gap at x3. So band gap at x2 distance will be wider than x1. Is it right?
Yes.
But narrower than x3. This is right, no?
Correct. Yeah.
Yeah. You understood why?
Yes.
Yeah, cool. And
That's the only answer, right?
yeah, band gap at x2 will be narrower than x3. That is false. You can see, right, from this diagram.
Yeah.
Yeah,
Band gap at x2 distance will be wider than x3. That is also false.
yeah. What about this? Free electron approximation and tight binding approximation lead to the same result, but originated based on different concept. So later concept means the tight binding approximation is based on dash
Strong atomic bonding approximation,
yeah.
and is not so relevant for semiconductor system.
No. See, tight binding is relevant for semiconductor and insulator.
Insulators. Okay. Not for.
For metallic system,
Metals.
free electron is the one. Okay, so it is strong atomic bonding and metallic. So tight binding is good for semiconductor and insulator.
Sure, sir.
And what is that? Free electron for metal.
Metals.
What about this fourth one?
Charge carrier concentration. This is temperature.
So just now we
consists of
discussed
dash regions and dash regions in case of intrinsic and extrinsic.
So here there
4
was
and 3.
4 and 3. No, we saw, no. See, if you increase the temperature, then what will happen? There will be a freeze out zone, then there will be a extrinsic zone.
Yes.
And for intrinsic semiconductor, it is just this. Sorry, this, and suddenly it will increase like this. So only intrinsic. This is only one region for this, but for this we have freeze out zone, freeze out up to this zone. This is called extrinsic zone, and this is intrinsic.
3 zones.
So it is three zones for the extrinsic semiconductor. So wait, let's see. Intrinsic and extrinsic. Intrinsic it is just one, extrinsic it is just it is 3. So it is 1 and 3.
Third answer.
Okay. What about this?
Average electronic conductivity of a metallic system is twice, right? 2 times, right?
2 times. How do you get 2? It is a metal.
Average electronic conductivity. Okay.
Yeah.
Is electronic conductivity more than the
Yeah, correct. Because
more
it is a
than
metal.
this?
Metal is more conducting than a semiconductor. Perfect. Okay. Now we can talk about this. Okay. What about this? Using the chronic penny model, a finite well potential system, dash are the parameters which will vary even after fixing the physical crystal structure and specific atoms in a matter. Okay. What about this? So I'll just draw a chronic penny model potential. In the meantime, you think what will be the answer? The system constants, what are these? A and B are your system constants.
Yes.
What about potential depth?
Alpha and beta, right?
Yeah, correct.
Alpha and beta will change.
Yeah. Alpha.
With that, depth will not change.
Yeah,
Lattice periodicity will not change.
Yeah, this is correct. Yeah, perfect. What about the second question?
Bloch's theorem discusses about the wave function at a lattice function x and x plus a. X and x plus a, that's true, correct.
Yeah. And what is the relation? This is the relation if someone asks you. Okay.
Yeah. E
Okay.
or ik.
What about okay, now we'll discuss this. Okay, doping and this I hope you remember we just discussed.
With a p-type dopant.
So
Dash
intrinsic
the
will
Fermi.
look something like this, no? The Fermi energy is, so I'll just draw here again. So this is your totally filled thing. This is your extrinsic. Intrinsic. This is your, this you want to dope with p-type dopant. Now this is your Fermi level EF for your
50%. Yeah.
now if it is just this dotted line means nothing. Okay, now where will be the Fermi energy for this if it is a p-type? P-type means just remember that it is group 3 elements are dopants.
Yes. So Fermi energy will be the border, right, in the
Yeah, towards conduction
H.
or towards, if you
valence
remember,
band.
huh?
Towards the valence band.
Yeah, towards the valency band. You see, it is towards the valency band. Okay, here, this diagram. EF is here. So your correct answer is 8. So what will be your answer out of these 4 options?
It is lower.
It lowers. And becomes discontinued, shifts.
Ships also, right?
Yeah.
Ships, yeah.
Okay. What is the fourth answer of fourth question?
Tight binding approximation differs from this thing is approximation its approach because in the former electrons are not exclusive to the atom. Tight binding it is exclusively bounded to the atom, correct? In the former electrons are bound to each atom. Atoms are brought closer
Who
to
differs?
determine.
Huh.
Second, 3 is not true. A sea of electrons roams through a lattice of fixed atoms. That is also not true.
This
That
is
is a
not
free
true.
electron.
Atoms are brought closer to determine effects of.
That is not true.
Mm, yeah. Why it is not true?
But it is
Atoms are brought together, no? When only when they are brought together, then only so we can
binding happens. Okay.
see. Another thing is electrons are not bound exclusively. Is it correct? If first is correct, how can second be correct?
Exactly. That's what I was even thinking. How can these two are contradicting statements? Yeah.
Yeah.
Electrons are bound to each atom is correct.
Yeah. So this is correct. What about the third one? So this is not correct, no?
Basically binding approximation, so it is brought closer.
Yeah.
Is it? Okay.
Okay. So what about the next question now? Let us assume
Let's
that in a
assume that in
material.
material.
Let us assume there are three energy levels E1, E2, E3. So you have three energy levels E1, E2, and E3. E1,
Yeah.
E2, E3. What will be the sequence of energy level splitting when interatomic spacing is steadily decreased? So what would be the sequence? First, which one will be first which one will split? So as you go from here to here, so what it is asking is, this is interatomic spacing.
Space. Yeah.
Atomic spacing. As you travel from, so this is your, sorry, as you go from here to here, what? It is steadily decreased. As you go from here to here, first which of the level will, what is the sequence of energy level splitting? So you are going like this, you are going like this, you are going like this. First which one of this level will split as you decrease the energy level, as you decrease the interatomic spacing?
E3 first.
First E3 will split, then what will happen? Then your E2 will split. Why it is happening like this? Because E3 is the outermost cell, right? It is the outermost cell. First
Valence.
they will start to overlap with each other. Okay, so first, so your correct answer is
E3 to E2 to E1.
E3, E2, E1. Okay, correct.
The free electron theory dash is explained administratively using equilibrium atomic spacing. Band bandwidth
Yeah.
and band gap also we can say.
Yeah, band gap also, because if you know the bandwidth here, you also know the band
Then
gap.
band gap.
Yeah.
Yes. Atomic mass and atomic number are not related, right?
Yeah, these are not related. Okay. What about this?
Band gap with increases with increase in pressure.
So you have two diagrams
Band
to.
gap.
So this is interatomic spacing,
Other one is the pressure diagram.
and the
Right?
another one you had this pressure.
Yeah. With pressure, band gap width actually decreases usually.
Yeah, with increase in pressure, band gap is decreasing.
So
band
decrease
gap
band gap width increases
increases with
decrease in pressure.
decrease in pressure.
Decrease in
What about interatomic
or
spacing?
increase in interatomic spacing.
Or increasing interatomic spacing. Correct. Okay. Question number 8.
Free elec free electron approximation addresses the existence of anisotropy in a material based on different locations of brilliant zones. Yes.
Existence of, yeah, different locations of Brillouin zones. Yeah, correct.
Correct. And different unit cell volumes. That is also correct.
How?
Because unit cell is different, right? Unit cell is same.
Unit cell volume. It has to be same, no, crystal, because you
Correct.
are
Yeah.
repeating that same unit cell over and over and again to generate that crystal.
Different crystal structures in different direction is maybe not true.
It is not true, no. Different crystal.
Yeah, I
You are
think this is
just
only.
given a material, you have one crystal system,
Yeah.
and the crystal structure is same given a particular material.
Yeah. I think it's only answer.
Yeah. That is the only answer. Okay. What about this? So
Which material
and
has less conductivity at room temperature than that of uh, significantly higher temperatures? Less conductivity in silicon, gallium arsenide. Gallium arsenide is a compound. It is a material.
which material has less conductivity at room than at significantly higher temperatures? So room temperature is what? 300 Kelvin. Higher temperature is,
Yes.
let's say 400 Kelvin.
Maybe like anything more than that. Yeah.
Yeah. Something, anything greater than 300. So we want conductivity at this T greater than 300 to be more than T at 300. How is this possible? This is possible only in semiconductors.
Yeah.
Which are the semiconductor?
Gallium arsenide and silicon.
Yeah. So these are your only two answers. In metallic systems, what will happen is, so see, sigma is equal to
It will increase.
Ne
Yeah.
mu. In metallic systems, what will happen? Mu will decrease. Even in semiconductor, mu will decrease.
Yes.
But what happens in semiconductor is N will increase so much when you increase the temperature, and it will increase
Yeah.
so much so that it will compensate for the decrease in this mu. So
Yeah.
on an overall, you will see in semiconductor, because of this increase in N, sigma will also increase if you increase the temperature. Okay.
Yeah.
Okay. So what about the 10th question?
What happens if the energy of electromagnetic radiation incident on a material is lower than the band gap of the material? Band gap of the material.
So just to give you the perspective, you have this thing, you have this thing, and the energy of the electromagnetic wave is, it is less than the band gap. This is h nu and this is Eg. So can this photon be absorbed?
H nu. No.
It cannot be absorbed, so it will just go through the material. It will have no effect on it. So
Okay.
the radiation gets transmitted through the material. Okay, so the radiation enables electron transition from valency band to conduction band. That cannot happen. That will happen only if h nu greater than Eg. But we are given that
Yeah.
h nu is less. It is
Less,
lower than
yeah.
the band gap. So this is not the correct answer. What about the material absorbs the incident radiation? It could have absorbed if h nu greater than Eg.
Greater than Eg.
So this is
Yes.
also not correct.
Even equal to Eg also it may absorb.
Yeah, even equal to Eg also it will absorb. Oh, the radiation increases the charge carrier concentration in conduction band. Can it? Is this true? See, h
Radiation
nu is
increases
less than
alkaline
Eg.
condition.
It cannot give this
Conduction band, it is not going there, right?
It is
It is
not
only in the
going,
valence
so
band,
this
right?
is also wrong. So this is the only correct answer. Okay. Okay, so we are done with all the questions for today. Thank you so much for
Yeah.
joining.
So a couple of questions, sir.
Yeah, sure.
See, in the band structure we did right now, we had P1, P2, P3.
Which one?
So when we P1, P2, P3 with the pressure diagram, you just did, yeah, the previous one.
I think this one. Pressure diagram. This one, I guess. Or which
Increase in
one?
pressure with increase in pressure. You just did it in the question. Yeah.
This one, it looks like P1, P2.
Yeah. So when we say P1, when P1 is the less and P2 is more, then insulator is within the P1. Correct?
Yeah.
Yeah. So basically, we have to say that with the increase in pressure, we see more conduction. So it will get into conduction mode.
Yeah. If you increase pressure, it will get towards being a conductor.
So basically, in the band gap calculation that we are using with time dependent Schrodinger equation at x0 v0 we did, right?
Yeah.
So we are considering that nearly free electron approximation with the condition that it is basically wave function and its slope are continuous at x equal to 0. Correct?
What? Can you repeat that again?
In the Schrodinger time dependent Schrodinger equation that we
Yeah.
solved
Mm-hmm.
at x equal to 0 and v equal to 0, in
Yeah.
nearly free electron approximation, we assume that slope and its wave function are continuous at x equal to 0, right? Or wave function and its slope are at x equal to 0. How do we
Yeah,
consider
that doesn't have to do with this particular diagram. That has to do with
not this diagram, Schrodinger equation. Yeah.
Schrodinger equation. Yeah. In Schrodinger equation, what we are doing? The wave function is continuous, and the slope of the wave function is continuous. You see?
Yeah. So the wave function and its slope.
Yeah.
Yeah. So basically, that's how it should be because it's a time independent or time dependent, sir.
This, what is the you see, this is the
No t, no. There is no t there.
there is no time. This is time independent Schrodinger equation in one dimension.
Yeah, it's a time independent Schrodinger equation. So when we say silicon, you said it is an intrinsic semiconductor compound, right?
Yeah.
Is it do we classify that into kind of a 2b 6a something like that?
2B.
3b 4a.
It is
2b
group
compound
4
or-
element, no? Silicon.
Yes. So okay. How do we define N and S, sir? N and P silicon. Which type it is?
N and P silicon.
Yeah, N silicon and P silicon.
Okay. So so how
Both
do
are
we get
intrinsic. With,
No,
for
how
example,
can-
N is
no, no,
having
no.
a band gap.
See, silicon is an elemental. So no, I think you are messing up something. See, what we are doing is, here we are taking silicon, and then we are doping with. So how do we get this N type? Uh, so what we have is silicon, right? Silicon, it will be bonding to silicon. So there will be, each silicon will have 2 electrons. So this will again bond with 2 electrons here. Here it is bonding with 2 electrons. It is bonding with 2 electrons. This isn't okay. So this is how it is bonding, and these are covalent bonds. So these are covalent bonds. So this is again, like, I hope you are getting what is going on here. So now if one electron will start to move around, so we, if you remove one silicon, let's say I am removing this silicon and replacing it with let's say arsenic. Arsenic has 5 electrons. AS, right? AS, yeah. It has 5 electrons. then in these bonds, what will happen is there will be one more extra electron which will be hanging around.
Yes.
So this is your n-type silicon.
Yeah.
Okay, it is doped with
Arsenic.
an element from group 5.
Yeah.
Okay, in p-type semiconductor, what will happen? Silicon and let's say silicon, so what will happen is, you see, it has gallium will have only 3 electrons.
Yeah.
Okay, this silicon will have 1, 2, 3, 4. This silicon will have 1, 2, 3, 4. This silicon will have 1, 2, 3, 4. This will also have 1, 2, 3, 4. You see, this silicon will have also 1, 2, 3, 4. You see, this bond will have 2 electron, this bond will have 2 electron, this bond will have 2 electron, this silicon will have also 4 electrons. But here you see, here one of the electron is empty. So this silicon will have 1, 2, 3, 4. Here this bond has 2 electrons, this bond has 2 electrons, 2 electrons. Here one of this is empty. That is a hole.
Yeah.
Okay, so this hole, so if the holes are there, this is called p-type silicon. This is an extrinsic semiconductor with and how do we get that? It is when it is doped with group 3 elements. This is an extrinsic semiconductor. So both of these are extrinsic.
Both are extrinsic, not intrinsic.
Yeah, in intrinsic there is no doping at all.
So when we say band gap, how do we calculate intrinsic semiconductor band gap? For example, indium antimony, INSB.
See, so that is an intrinsic. There is no doping at all. It is a 3-5 semiconductor.
No, where is the band gap? Band gap, how do we calculate?
Band gap, how do we
INSB.
calculate? I mean, I'm not understanding. The
How do, if for
Okay.
indium and antimony, if I have to calculate band gap, how do I calculate it?
Okay, so there is
Formula?
yeah, but I'm not understanding the context of your question.
Basically, indium and antimony, you are saying intrinsic semiconductor. If I want to calculate the
No,
band gap
indium
of
and
this
antimony are not individual semiconductors. They are
no, it is together as
semiconductors.
an intrinsic semiconductor.
Yeah, the compound indium. So we talked about this, no? Oh, that is not. 3 types of semiconductor. Somewhere here we discussed. See here, it is a, so you can look for the value of band gap. It can be calculated by, there are different methods, like experimentally you can determine by absorption experiments, or so there are
But
different
gallium arsenide,
so
sorry.
these are intrinsic semiconductor. They do not have any impurity or defect level.
Okay.
As soon as you have impurity or defect level, then what you have is then you say those are the extrinsic semiconductors.
Yes. So basically, my question is, how do I calculate band gap for this in case I want to do it? Any formulas?
Yeah, there are different techniques. Okay, so but what is your input? What are the information you have at hand?
Okay, I have only say indium and semiconductor antimony, and I say that my valence electron. This is actually a compound, right? How do I get a band gap of this compound? That's my question.
See, you can calculate for this EK diagram. From that EK diagram, you have to look at the conduction band, and so you have to look at the what is the highest energy level, then what is the available energy band just next to it, then you subtract that. So that is how you get the band gap. So your task is to find that EK diagram, either the EK diagram or this flat band structure like this. Then you subtract this energy level. So that can be found by, there are different techniques. There is density functional theory. There are other analytic.
Oh, so I have to use a DFT. Okay.
What?
DFT theory. DFT theory.
Yeah, some DFT techniques are there. So these are different techniques available at hand. So theoretically, if you are given a crystal, then you can find what is the band gap diagram. So these diagrams that you see, this we drew, that actually you can get from DFT for real material. Okay, from there you can see up to how much the electrons are filled. Then you can subtract this and find the band gap. So that is a method. So you don't
Germanium
have
also is an intrinsic semiconductor, but can you call this as an intrinsic semiconductor compound by itself, or is it a 2B4A compound? Germanium.
Germany is,
Germanium is an intrinsic semiconductor, right?
yeah, it
No
is
doping
intrinsic.
is needed. But can it call it as 2B4A compound or only 4A, group 4A?
2B 4A. Why is 2B coming into picture?
2B is only when we do extrinsic, is it? Anything like that, nothing. 4A is, group 4A is silicon and germanium. No
Yeah,
doping.
yeah.
Gallium arsenide and antimonide, this thing is 2B and 4A. Okay, I just had this question, general, and also sir, in the last this thing also, when brilliant zone, when we say
Yeah.
different distances and different direction,
Hmm.
so which means that we are talking about having an anisotropy.
Anisotropy. Yeah, that's right. No, different direction. If the brilliant zone is, so we did this diagram, right? These are different directions.
Yeah. Different direction and different distance.
Different distances. Yeah. Like for example, here the periodicity is, let's say, pi over A1. This can be pi over A2, depending on what is the periodicity your electron is seeing.
So when we say this, it should be only a metal, or can have a non-metal also with different distance and this thing.
I didn't get your question. Can be a metal.
Can it have the similar condition for metal or the semiconductor also, or only metals can have this condition?
Which condition?
Brilliant zones of different boundaries and different distance.
Different. Hey, anything
different,
can happen. Like it depends upon the crystal structure. Anisotropy is a property of. So it depends on what is your crystal structure of the metal. If you have an anisotropic crystal, then you will have a different.
So only metal only can do like this, or can even semiconductor have this kind of different?
Yeah, even semiconductor can also have, no. There is no rule that. For example, silicon is an indirect band gap semiconductor.
Yeah. So in this direction, for example, interatomic distance will be different, sir.
Interatomic distance will be different. Interatomic distance, why?
Interatomic spacing. It's the same, right? Always.
Yeah, interatomic
Because
spacing.
we have different direction.
So no, interatomic spacing will be different for different directions. For example, if you have a cube, let's say. So let us take it in 2D only. In 2D, what is the interatomic spacing along this direction and along this direction? The interatomic spacing are different, right? Here, if it is A.
In different directions, yes, it's always different.
In this direction, it is root 2A.
But in the same direction, it will be same.
In the same direction, it will be same, yeah.
Sir, one more question. In the last class, actually, I had this. But before that, gallium arsenide is intrinsic. Actually, I wrote it down somewhere when you were explaining it. Gallium arsenide is an intrinsic semiconductor.
Yeah, it is intrinsic, yeah.
And is it a direct band gap or indirect band gap?
It is a direct band gap semiconductor. Gallium arsenide.
How we say direct and indirect, sir?
Yeah. So the way we say is we have to look at its EK diagram actually. In the EK diagram, I will just show you how the actual EK diagram looks like. Uh,
But that is not covered in our portion, was it?
yeah, but I don't know why are you asking about that, but it is not covered in the course.
No,
But
because I actually noted down some of this because when I was reading through some old questions, I was just going through all this. I thought I will ask you these questions.
yeah, yeah, but gallium arsenide EK diagram is this. So, so you at least you know about the direct band gap and indirect band gap thing, right? So I will.
Yes.
So I told you two statements, right? Silicon is an indirect band gap semiconductor, and gallium arsenide is a direct band gap semiconductor. So if you look that EK diagram, let it just come up, yeah. And I will put another one in which EK diagram of silicon. Hmm. So just to give you some context, okay, EK diagram. So what we had seen here in this PPT, what we saw was the base of this. So the next immediate. So for example, you can see my cursor, right?
Yes, sir.
Yeah. So from here, if I go up, then the next nearest energy band is not at the same k value, it is at a different k value. You are getting it? That is what it,
Can you
so
repeat,
that is
sir?
what is an indirect band gap semiconductor. So an indirect band gap semiconductor, this is your valency band, and your next immediate energy level is at a different what is that, yeah, it is at a different k value. But for a direct band gap semiconductor, this peak and this dip are coinciding, or they are at the same k value. Okay, that is your direct band gap semiconductor. If you look at a silicon, if you look at the diagram of silicon, let's say this diagram, then you see, where is the diagram? Yeah. Do you see that peak is here, somewhere here, and the dip is at a different k value? This is for silicon. That is why, and this diagram you get from let's some DFT calculations or some other calculation. So what you have is, since the k values are different, this is your indirect band gap semiconductor. But for gallium arsenide, the tip of this is same as the, sorry, the peak of this is same as the dip of is located at the same k value as the dip. That is why you say that this is a direct band gap semiconductor. This is clear, no?
Yes, sir.
So indirect band gap, you can just silicon is indirect example, and direct band gap example is gallium arsenide. Okay. Yeah. Any more questions?
In the last class, sir, last uh, class, we went through one question.
Yeah.
In that, actually, I had one question. I'll just open up.
Yeah. Which question?
Just a moment, sir. I'll just open that up.
You are able to see the slide, right? Okay.
I can see. I'm just. I noted down. I'm just trying to see. Can you go to the next one, sir? Next question, 41.
Yeah.
Here we discussed on this particular question. Which one was that?
You can read out the question.
Yes, sir. Yeah. Wherever diffraction condition is satisfied or diffraction occurs,
Yeah.
certain values of energies are. Diffraction occurs and
Okay.
This one. Yeah,
This
here.
one.
This one. So we said only forbidden, right, Nasir?
Yeah.
Okay. So discontinuous is not possible.
Discontinuous, it is
Because
energies
when we
can be
discussed,
discontinuous.
I remember we discussed both discontinuous and forbidden.
Yeah, discontinuous, like this was a bit vague. I mean, I'm not sure what this word means, but maybe you can. So what happens is, like, the point for you to understand is this. So it was earlier like this. Certain values of energies are discontinuous. Energy being discontinuous, it doesn't make sense. So, energy, some energy are forbidden. They are not allowed in the system itself. So earlier it would be like this. I don't know what the question exactly wants to imply, but what it basically means is this.
Yeah, but we discussed on it. No, it is not continuous. It is going to be discrete in between. So
Oh yeah, yeah. This discontinuous. Yeah, yeah. Discontinuous means okay, okay. You mean it is? Yeah, these are not continuous. Yeah, correct, correct. It is not discontinuous. So
then why they only gave this only this answer? Because I think in one of
yeah,
the
yeah.
assignment also they
It
asked
is,
this
it is
question.
discontinuous actually, because values of certain these energy values are, these are not, you see that this is like this, but it is actually, so this would be an exaggeration, but it is actually this.
Yeah.
So this is discontinuous would be correct, no?
Correct. Yeah. But for some reason, no, in one of the assignment they had asked this question. I had given both answer, forbidden and discontinuous, but they gave only one as correct.
Okay, maybe that discontinuous they mean that thing.
I don't know.
This
The second also, no, there is one more question. I don't know whether we did it in our assignment. This thing, you see in your questions, if it is there, uh, in a diagram, potential energy, which is position diagram, we were talking about different zones.
different
I
zones.
don't know whether you have it in your assignment, but we discussed in the this thing course, but in the assignment, I don't know whether we saw it.
Okay, what is the question?
Uh, if you can open the assignment number 11, sir.
11 is today,
No,
right?
not 10. 10, 10.
Yeah, 10 is this
10, sir.
only. Huh. What is the question?
No, the question is about a small diagram they have given, and in that A, B, C, D, and E, they are talking about different brilliant zones and this position, potential energy and position, like what we did in our course. Yeah, this one exactly. This itself, but this is mainly K and E, right? They are talking about different zones that were marked, very similar to same diagram. Only thing the questions were different. The questions were saying that A, B, and C brilliant zones. Basically, they gave A is the 0 to pi A, that location,
So yeah, the first, okay,
0 to
okay.
A.
Uh-huh. So what are the
0 to
Brillo
A.
zones here? Yeah, this is
A,
what,
B, C.
this is
Now, if
your
you see the
Brillo.
blue color zone,
This is one Brillo zone. The other Brillo zone is shown in this green. This is another.
green,
Yeah,
yes, yeah, that is B,
yeah,
B, and yellow is C,
yeah,
right?
yeah.
And then they have given D as C, the boxes that you have made, the square boxes that you have made outside, which is, forbidden bands.
These are the forbidden bands.
B, that is the D, that is D, and
D.
E is the dotted lines, that is the dotted lines between pi A and 3 pi A, the red dotted lines that you have made, pi
Pi
A
A.
and the vertical lines, pi A, 3 pi A vertical lines,
Okay, okay.
that is E, that is E.
The region between
Okay,
these two.
so now, no, the location, yeah, you can say like E, that is called E, they are given it that as E, dotted lines as E,
Okay,
you can
okay.
mark it as E.
Okay.
So now A, B, and C are our brilliant zones, right? First, second, and third brilliant zones.
Yeah, yeah. That is true.
And D, that square boxes, that the brown square boxes, that is called forbidden bands.
No, these are allowed bands. Forbidden band is this one. The gap between these two.
In between.
Yeah.
Ah, okay. Then I made the mistake. Okay, that's energy band. And can we call this perpendicular bisectors as this one, the 4, pi a and 3 pi a as perpendicular bisectors? Is it?
Pi a and 3 pi a are the perpendicular bisector. Yeah, they are the perpendicular bisector of. Uh, they are the perpendicular bisector of this thing. No, what it is called?
That's a Bragg plane.
Yeah, that is
Bragg
a.
plane.
See, 0 to 2 pi by a. That is what. For example, if you have a this is your real lattice. Let's say
Yeah.
this is periodicity. What would be the reciprocal space of this? In reciprocal space, you will have again a linear crystal but with gap as 2 pi by a. Now you draw a
Yeah.
Wigner seed cell around this. How do you draw? You join, you choose one of the atom, take it as origin. Then what you do, you have to perpendicularly bisect the line joining this lattice points. When you do that thing, this is your Bragg plane. This is your Bragg plane. So if
Yes.
it is 0 and this is minus 2 pi by a, so this will be minus pi over a. This is pi over a. Then another one will come at 3 pi by a. So these are your Bragg planes. So similarly, this pi a and 3 pi by a, these are your Bragg planes.
Yes.
Yeah. They are the
Correct.
perpendicular bisectors of.
Yeah, I think I made that confusion. Bragg planes, forbidden bands, instead of energy band diagram, I said forbidden bands. I think that is my mistake.
Okay. I hope now it is clear.
But yeah, the other question was only the confusion. The discontinuous word was, they
Yeah,
somehow took it
the
as,
discontinuous, it really means that discontinuity of that energy in the band or formation of that band gap. That is a bit vague.
so reciprocal lattice plane is, when we do it, basically it can actually find the Bragg plane
Yeah,
and
it can.
then
Huh.
Brilliant zone.
Hmm.
From real lattice to reciprocal lattice to Bragg plane to Brilliant zone. Or we can say identifying the innermost region in Wigner cell to the Brilliant zone, or dyeing Wigner cell to the Brilliant zone. Anything we can say, sir.
I'm not understanding. Can you repeat that again? See,
When we say real lattice, from real lattice to reciprocal lattice,
from
then
real
we go
lattice
the
to
stepwise,
reciprocal lattice.
reciprocal lattice, and then before going to the first Brilliant zone, we have to identify the Bragg planes.
We have to identify the Bragg planes. Yeah.
We have to identify the innermost region in the Wigner cell.
Yeah, the innermost region in that inner cell. Yeah, the region of the space. The region of the space which is bound by these Bragg planes, it is called, like for example, you want to find a Wigner seed cell about this particular atom, then you have to find the region of
Yeah.
space which is closer to this atom uh, than any other atom. That you can find
Yeah.
by constructing, making this Bragg plane construction.
Okay.
Yeah.
Yeah, I think that was one question I didn't quite well answer it. I answered for the only. I thought it's only one answer. I answered it only
Okay.
drawing Wigner cell, because that is the obvious one. Drawing Wigner cell is what we do.
Yeah.
But identifying the Bragg planes, identifying innermost region in the Wigner cell is also part of the answer.
Yeah, true.
Okay, sir. I think that much. Thank you so much, sir.
Okay, no problem.
So after next week is the last week, I think, sir.
Yeah, next
After
week is
that
the
week,
last week.
we'll have one class for revising or no?
If you want a revision class, that also I can take, but I don't know what to discuss in that. So if or if you have some doubts in the entire course, that I can go through, or you can ask the
Yes, sir,
question
and-
like we can
And
schedule
also
a
we can
revision.
go through, we can go through all these questions we went through, right? If you can go through one more time from either the assignment portion or from your question bank,
Yeah,
if you can go one more time, that will refresh the entire subjects.
yeah, we can do that.
I think you didn't record or you're recording? I didn't say.
Yo, it is being recorded till now.
Oh, okay.
Yeah.
Because I didn't see it.
Yeah.
Thank you, sir. I took extra 20 minutes today. Sorry.
Yeah, no problem. That's totally fine. Okay, thank you.
Thank you, sir.